Okay, in the last video, we worked with a region that was essentially over a simple YZ solid. So we projected onto the YZ plane instead of the XY plane. So we were just doing our integration in a slightly different order. This video is going to focus on that basic idea. Okay. So I've set up an iterated integral here where we're integrating first with respect to z, then y, then x. That tends to be the order that I'm used to doing things in. What I want to do is I want to Fubini-ize. I want to change the order of the integration. I'm going to reverse it so that I can do x first, then y first, then z first. But I know I can't just switch these limits around because they're not all constants. And remember, the rules are here you're allowed to have a function of two variables, and it's allowed to be the two that you haven't integrated with respect to yet. Here you're allowed to have a function of the one variable you haven't integrated with respect to yet, and here you've got to have constants. So what we're going to have to do is go from these limits of integration to visualizing the region that we're working over, to then describing it in terms of this order of setting up the integration. Okay. So I'm going to work through that in this video. I'll leave it up to you to decide whether you want to try that on your own first or not. We're basically just looking for what are these limits of integration. If you want to pause the video and give this one a shot on your own, you're more than welcome to do that, and then turn the video back on to check your work. If you feel like you're not quite sure where to start, just keep watching and we'll work through this together. You'll have examples similar to this in the homework that you can practice on your own. Okay. All right, so I find it really helpful with a triple integral to think of it as a double integral followed by a single integral. If these are my z values, that tells me that this is the bottom surface and this is the top surface. And this is just describing my region D in the xy plane. Let's actually start with D. So in the xy plane, let's see, these constant limits of integration are my x values. So I know that x is going from 0 to 2. So I've got the y-axis and the vertical line x equals 2 are my left and right boundaries. Then my y limits of integration are 0 and 2 minus x. So here's y equals 0. 2 minus x is just going to be a line whose y-intercept is 2 and whose slope is -1. And that's kind of nice because that's going to intersect the x-axis right here at this point where x is equal to 2. So D, it turns out, is just this triangle right here in the xy plane. Okay. Now, let's look at our z limits of integration. The bottom surface is 0. That's just the xy plane. So our floor is this triangular region in the xy plane. The top surface is this. That means that the z is equal to 2 minus x minus y. Okay. That's just a plane. I'm going to add these pieces over. That just means x plus y plus z is equal to 2. And I want to try to find the portion of that plane that lies above this. I'm going to use this nice trick that I'm just going to see where we intersect the x, the y, and the z axes. Okay. And in this case, I can see I'm always going to intersect in a positive place. If I had a plane that was intersecting an axis on a negative part of the axis, I would draw the negative part of the axis instead of the positive part of the axis. Funny how that works. Okay, so on the x-axis, y and z would be 0. So we're going to have x equals 2. So there's the point 2, 0, 0. Similarly, on the y-axis, x and z are 0. So I would just have y equals 2. So there's the point 0, 2, 0. And then on the z-axis, x and y would be 0. So z is 2. So there's the point 0, 0, 2. So it looks like we're actually working on this tetrahedron here, where this is a triangular section of the plane, z equals 2 minus x minus y, that lies above, oh, and isn't this nice? If I look at this triangle right here, that is exactly what we got right here. That's my D. Because in the xy plane, I just wouldn't have the z values. We were connecting the points 0, 2, and 2, 0 with this line right here. Excellent. So that's the region now over which we're integrating. I've got a nice visualization of that. I'm going to stop calling that D, because now I want to find my limits of integration here. And so I'm going to be projecting onto the YZ plane instead. So that's going to be my new D. Okay. That's going to be what I describe with these limits of integration. And then these limits of integration will be the back surface and the front surface. Notice I can't really do this problem without visualizing this region, okay? Because I can't just say, oh, these z values are going to go to these z values, because these z values were functions of x and y, but these z values have to be constants. So I have to see what the region looks like. But now with x, we're going from back to front. So I can see the back surface is what I have in the YZ plane. That would be when x is equal to 0. The front surface is this plane here, which we said was x plus y plus z equals 2. That's now my front surface. And what I want to do is, instead of solve it for z, I want to solve it for x. So that's x equals 2 minus y minus z. That's going to be this upper limit of integration. Now, these limits of integration are going to be describing this triangle D in the YZ plane. So let's just draw our two-dimensional picture of that here. And let's see, if I wanted to do dy dz, that essentially means that I'm going to be slicing things this way, because the z limits of integration have to be my constants. That's going to be the numbers where the slices start to the number where the slices end. Looks like that's going to be from 0 to 2. And then for each slice, we're going to integrate with respect to y from left to right. Now I can see the left boundary is y equals 0. Let's just get an equation for this line. Okay. I'm going to start by solving it for z, because I'm used to solving for what's on the vertical axis. So I would say z is just 2 minus y. It's got a z-intercept of 2 and a slope of -1. But because this limit of integration has to be y as a function of z, I just need to now solve this for y. So I'm going to add over the y, subtract over the z. Y is going to equal 2 minus z. So we have Fubini-ized, and here are our new limits of integration. They do look fairly similar to this, and that's simply because I've got a lot of really nice symmetry here. The triangular cross-section that I have in the xy plane is the exact same size and shape triangle that I have in the yz plane, is exactly the same size and shape triangle that I have in the xz plane. That won't necessarily always happen. Again, you really can't just look at this as a pure algebraic problem and figure it out. You really need to explore the geometry of the region over which you're integrating. Okay? That wraps up this section for us.